Hello, Papa. Yeah, Kirtana, can you hear me?
Yes, sir.
Okay, Kirtana. So yes, we are supposed to start a new chapter, magnetic field of current.
Yes.
Mm. Have you studied this chapter earlier?
Yes, sir.
Okay, so I hope you might be having idea about this chapter a little bit, right? So, should- okay, so basically, Kirtana, this chapter is quite big. So in the first part, we'll be discussing about if there is a current, how a magnetic field will affect. Okay, what is the effect of current in producing a magnetic field? This is what we are going to study in the first part, and after this, we'll study about the maybe laws. Okay, how you can use magnetic field. These two things we are going to study. Okay. So if I ask you what is magnet, magnetic effects. Okay, so basically if you see carefully, we have two different magnets. Okay. I'm not going to take a magnet. I'm saying I have two different electrically neutral bodies. Okay, what I'm saying is now, if you have two electrically neutral body, can you tell me what I meant when I say electrical neutral body?
The charges
Charges?
are equal.
No, exactly not. When we say something is neutral, we have two phenomena of electric, right? Either thing can be positive, either thing can be negative. And the third is neutral state, right? Neutral means to say this net charge is zero. So when I'm saying there's a two electrically neutral body, mean to say net charge is zero. And if they are able to attract on repel, if there's some force of attraction, maybe on each other, maybe something like this. So this comes up due to the magnetism, okay?
Yes.
So basically I'm saying you have two different electrical bodies. If this F, this whatever the force is, this force is called magnetism, magnetic force. Okay. Okay. So what I'm saying is now, if you have two electrically neutral body, and if two electrical electrically neutral bodies are capable of attraction, of attraction and repulsion, then you can say this is due to, then it is due to, it is due to magnetic force. Okay. Is it clear, Kirtana? Why I'm calling it magnetic force? Kirtana, do you think this definition is correct? This is correct basically about magnetism.
Yes, sir.
Okay. Um, okay. Can I say this thing can also be happen due to the gravitational force?
Yeah. No,
Just
sir.
think of it. Why?
The gravitational force just pulls it downwards. Does not attract or
Wait. Just think of it once. What you said. The gravitational force just pull down. Is it? Okay. What is gravity? If I ask you, what is gravitational force? Can you explain me what is gravitational force?
That attracts things towards.
Attracts things toward. Basically, any two bodies in universe, it's a law. Okay, it's universal law. That's why we call gravity as gravitation. Gravitation is a universal law because any two bodies in this universe attract each other. They should have mass. That's the main condition. Okay. So here, because I said they are electrically neutral and still they are capable of attracting or repulsion. Still they are able to apply some force, right? Whether it's attraction, whether it's repulsion. Okay, that's a different case. If this is happening, so I can simply say electric. This is not an electrical force, right? Because for electrical forces, you need charges, but there is no charge. Okay, I'm removing it. What else I can have? I can say gravitation, but wait, let me see. Gravitation force says that the bodies only attracts each other. There is no repulsion. But here the bodies can repel also each other. So what is the third? The third is magnetism. Okay. In that case, you can call it as a magnetism. There is some body. Assume now if I am going to put some charges on this body, does it mean that all the what I can say magnetic force was there that has been removed? No. Now you can say you have both effect. Okay, electrical forces also and gravitational forces. So for now, just remove this thing. Just assume we have two neutral bodies. Okay, we are discussing about that. No charges. Bodies are supposed to be electrically neutral. Supposed to be. See. Okay, if I ask you why magnetic field is there, why any material produces the magnetic force? Look, when I said the bodies are supposed to be electrically neutral, like net charge should be zero, but I'm not saying that charge inside should be zero. I'm saying net charge is zero. Assuming I have some body over here, okay. Let's say this is a body. What will happen here now? There will be some positive charges. There will be some negative charges. Okay? Even now, I can say the body is electrically neutral. Electrically neutral. So what I can simply say, even the body is electrically neutral, there is a charges. So movement of these internal charges, okay, provide you the magnetic effect. Is it clear?
Yes,
Okay. So I can simply say the cause of magnetic force is the motion of charges itself. Okay, motion of charges itself. Now you will say, sir, we had the same thing that if the charge is moving, I can say current is there. If the charge is moving, magnetic force is there. That's exactly the same because a moving charges will produce both things. Okay, that will produce electric field as well as the magnetic field. So, a moving charge, sorry, but the cause of magnetism is motion of charged particles. What's next? Okay, the bodies which possess proper property of magnetism is known as magnetism. As magnetism. Any body which has this property. What is the property of the magnetism? The body, if the body is neutral, even after being electrical neutral, it has tendency to apply force of attraction or repulsion. Then you can call it has magnetism property. And if it has magnetism property, you can call it as a magnet. Okay. So let's make a bar magnet. What we are going to do, assume I have a bar magnet like this. Okay. So in this bar magnet case, if you see, I'll just okay. So Kirtana, what will happen is, our Earth has a south and north pole, right? We assume on our Earth that one is north pole, another is south. Okay. So when you have bar magnet, bar magnet is what? It is nothing but a body which exhibits magnetism property, right? It has a property of magnetism. So whenever you have this kind of bar magnet, okay, whenever you have some kind of bar magnet, and what you are going to do, just take a thread, okay, thread. This is bar magnet. Okay, this bar magnet is suspended suspended freely. What I meant, you have just suspended it freely. Then, because it has a property of attraction and repulsion, so the pole, the point which is pointing towards the north pole. For example, assume this is a this these are two ends, right? The end which is pointing, let's say this is your Earth. Um, just somewhere. Assuming you are right now at this particular point, you are doing experiment. Okay, I'll make it quite big. So, assuming this was your north side, so yeah, assuming at this from here, this was your north side, this was your south side. So, what you said, north, south. What I'm saying is, you just they simply suspended it freely. The point which is pointing towards the north will be called as a north pole, and the point which is pointing towards the south is can be not called as a south pole of a bar magnet. Understood my point? What I'm trying to say is the point, the pole which is basically in a bar magnet, we say two pole, right? Two opposite pole. Just like in every case, we have a positive charge, negative charge. Two kind of charges are there, right? In this case, we can keep the poles charges separately. We can keep positive and negative separately, but here we can't do this. So the pole which is pointing toward the north will be known as north pole, another will be known as the south pole. Is it clear?
Yes, sir.
Uh, when keeping a bar magnet suspended freely, the pole pointing towards of Earth we call as north pole. Okay? Um, other one is south. Other is south. Okay, good. Now, so if you see carefully, what we are doing over here is No, yes, yeah. So if you see right now, I have a magnet, and in this magnet, I have two poles at the same time, right? One pole and this another pole. Okay. North pole and south pole together. South pole separately can be called as monopole. Okay. What are two monopoles? Basically, single pole. Separately are monopoles. So the single poles. Basically. Acha, if I ask you, Kirtana, I have a magnet over here. Okay, I suspended a bar magnet. Okay, then what I did is I had this bar magnet, and because this was a bar magnet, we were suspended freely. Assume this point was pointing towards the north. Okay, then you call this as a north, and then you call this as a south. What do you think, Kirtana? If I cut this bar magnet from in between, let's say I'm cutting it from here. Okay, not even from between. So what do you think? I'm going to get two new poles, right?
Yes.
Okay. This is one I'm going to get, and this is another one I'm going to get. So what do you think, Kirtana? The part which I'm going to get will be a monopole or dipole? Wait, dipole, I didn't explain you what is dipole. Basically, what is dipole, Kirtana?
Which have two poles. The south and north
Which
together
are,
are
yeah,
one.
basically, right? So assume that. So I wanted to ask, if I cut it into two, what do you think? Will this portion will only contain, because you can see south was here, north was here. So when I cut it from middle, what do you think? Will it only contain north? Will it only contain south, or will it contain both?
Both.
Right, both. If I'll just explain you a small reason. If you see carefully, this is a north pole, right, of a magnet. The moment I cut it, this north pole will still be pointing towards the north, right? So what about the other pole? This will still be pointing towards the south pole, okay? So here you can say this becomes a new south, and in this case, because this was the earlier south, it will still be pointing toward the south pole. And what about the other one? This will go to the north pole. That's very simple. So you can say you can, okay. So by this thing, this is north, this is south, north, south. So question is that, is it possible for us to get monopoly? What do you think Krishna, about this question?
No, sir.
You can say monopoly does not exist. Okay, this does not exist independently. Okay? They can only independently. This is one thing. Now, Krishna, very simple idea. Now I am saying I have two magnets. Okay? So properties, you can see small properties. Look it now. Just like I have North Pole, just like I have South Pole, just like I have North Pole, just like South Pole. If you see in charges, what happens is now positive, positive, negative, negative, positive, negative, negative, positive. If you could remember, in electricity we say like charges, oh, like, because they are like, right? They are with they will repel. Unlike atoms, right? So here also the same thing. Unlike, they are attractive in nature. Okay? Unlike poles, attracts. North, south, Uh, let's keep it south and north pole. And I don't see I really don't have to do the other part also. Here you have these as a what is it? Light. Okay, I'll just make it in a once. Let's make it quite big. Okay. So here if you see this is south, north, south, north. Okay. Unlike basically light poles, ripple nature. Clear? Is it clear?
Yes.
Okay.
Yes.
So this is all about a small magnet. Okay? It's not completely clear, but we just had a small discussion about the magnet. Okay? So let's talk about pole strength. What is the strength of a pole? So assume this is a north pole. It's not okay. Let's say this is a north pole and this is a south pole. Okay? We had a bar magnet and we are describing what is pole strength. So let's say I'm just talking about this. So the effect on around its environment, the effect of this particular pole around its environment is known as pole strength. Okay. What does this mean? Let's see carefully. Look, let's for these chapter we will try to go with the charges and take the analogy of that. Okay. So instead of this positive, let's say I'm keeping a positive charge and here I'm keeping negative charge. What does this positive? What is this electric field strength mean? It means to say that if I'm keeping a charge over here, what is the effect of it? If I'm keeping a bigger charge, it will provide more force, right? If the charge is less, it will provide lesser charge force. So same here. If if this charge, if this magnetic field, like if this magnet has a lesser value, it will provide a lesser magnetic field or strength and the same thing. Okay. So this is one thing. Okay, and one more thing, just like in a electric dipole, we used to have same charge. Okay, but what we say in dipole, electric dipole, we had a same charge but different configuration, like positive negative. Say here you can say this has a n, okay, pole strength n, it will be having minus. Okay, we can say this is just a value of a monopole. Clear? North pole, positive one, south pole, negative. Clear?
Yes.
If m increases, magnetic effect increases. M decreases, magnetic effect decreases. Look, the only difference is in case of charges, you can have a negative charge separately, you can have positive charge separately. But here in the magnet, if north pole exists, then on a same magnet, other side south pole will always exist with the same value, okay, just in a negative sense. Is this clear?
Yes.
Just the sense of charges will be negative and the rest will be the same. Okay, this concept is same. Yeah, one more thing, if your m is zero, then magnetic Like this is okay. What about this pole strength? Pole strength is basically scalar quantity. This is quantity. And what type we have? You can say we have two types. First is positive. You can call the positive as north, and like it's only basically north and south, but you can assume north as a positive and south as a negative. So whatever the negative charges do, the similar thing south will be doing. Positive or two, the same thing will be negative. North pole will be doing. Okay. If I talk about SI unit, so basically the SI unit is amperes meter. Okay, ampere meter. It's not per meter, it's just a meter. Okay, basically you might be doing I multiplied with the distance, something like this. Okay. Right now, don't ask about the derivation because whatever we are studying right now does not contain derivation for this particular part. Just remember that for the pole strength means basically just like a charge we had Q, right? The same thing, pole strength. Okay, what is the pole? Individual pole, that is M minus. Okay. So the unit for this pole strength is ampere meter. That's it. Just remember for it now. Okay, we will derive in the future. Why we are concerned about the SI unit because we need dimension also. So what's the dimension you can say? Dimension. That is I basically for the current, okay, and L. So from this, what is the dimension you are going to get? Ampere into length. This is what the dimension is. Okay.
Yes.
Just like in case of electric dipole, we had a term electric dipole, just like electric. Look, just like in case of electric dipole, when we talk about electric dipole, we had electric dipole moment, right? What was the electric dipole moment? Can you explain me once? Can you explain what is electric dipole and electric dipole moment?
Electric type, no?
Yeah. What's the meaning of electric dipole?
Two charges are there with a distance thing.
Yeah, exactly right. So if you see carefully, can I say in this particular case also, what I can see is I am having two dipoles. Okay, I have two dipoles having equal. Basically, it is M and another is minus M. Equal but an opposite configuration. They are separated by some distance L, right? And because the distance is very small, can I say we can relate it with electric dipole? If you see in electric dipole, we had a positive charge, just like this is a bar magnet. So I'll just remove it first. Let's move the topic itself. Magnetic dipole moment. Okay. If I ask you, Kirtana, what is magnetic dipole? Can you explain me once? Can you explain me what is magnetic dipole moment? Kirtana, can you explain me magnetic dipole? Not Not moment, just a magnetic dipole.
A magnetic bar.
No. Wait, what is monopole?
Monopole. The North Pole and South Pole separate.
Yeah. So what is dipole?
Both
Dipole,
North Pole and South
yeah,
Pole together.
exactly. On a single, because we can't actually separate the poles. So in this magnetism, the dipole exists. Okay, always dipole exists. Monopole does not exist. In case of charges, we can have monopole, and we if we want we can have a dipole. Also. That is the thing. So here we can simply say, if when we had, okay, I'll just keep a bar magnet first. So this is your north pole, this is your south pole. Okay. What I'm saying is, in case of, if you could remember about your charges, in charges we had positive charge and I had a negative charge. Okay, so we say there's a electric field from here. What was the dipole moment? The direction of dipole moment was from negative to positive. Right? If I say this is positive q, this is negative q. So dipole moment was from here to here. This is your dipole moment, right? Could you remember that? This was your
Yes, sir.
dipole moment. Right? Although this will get erased, the red thing. So here also we will be having a similar thing for this negative and for this s. Okay, we'll be having the same thing for this n and this s. What do you think? What should be the direction for your magnetic dipole moment? We call this. We call for this positive, negative. We call from negative to positive. There is something called dipole moment. Okay, we call this is a dipole moment. So what we will call for this thing? N and s. This will be representing your magnetic moment. Okay, magnetic dipole moment basically from south to north. Okay? Just like, because the total length you can say from here to here is length L. Okay, here we have dipole moment. This there we had the dipole moment. What was the value of dipole moment? Charge multiplied by the length. Okay? Here we have, here what we have, magnetic moment. What we call this as small n times of L. What is this n? The single dipole, single monopole, okay, multiplied by the length. This will give you the magnetic moment. Is it clear, Kirtana?
Yes, sir.
What is the direction of this?
South
South
Pole.
to north. Okay, I just explain it once. What is it? Magnetic dipole moment. What about this? Monopole. Just like that we had charge, we will call this as a monopole. Okay. If I ask you what is unit of this, so you can now tell the SI unit is nothing but what is M? M already we studied the unit. What is it? Ampere meter, right? That's why I told you about this. So this was ampere meter. Now you are multiplying this meter. Okay? So here you can simply call it as A M was earlier. Now you have added one more L, so it will become square. Dimension. It will be A L. This is your dimension. Mass is zero. That's fine. So far we have. So how the practical bar magnet is. This is whatever we have studied. Uh, theoretical bar magnet. Okay. Practically. In practical cases, now look. Earlier, I discussed that in theoretical, the north pole and the south pole exist at the very corner. So the total length is nothing but that basically the length, the virtual real length is nothing but some little bit less. Okay. In reality, what happens is these exist. This does not exist in the complete length. Okay. Assuming this is the total length L. Okay. So these will be little bit inside. Where it inside? From here to here. This is the real position. Okay. Practical. This is the real distance between two poles. Understood my point? Even though the bar magnet has the complete length of L, the real length is not L. What is the total length? The real length is 6 by 7 times of L. Understood? 6 by 7 mean to say, if you take this x, if you take this x, so 2x is nothing but 1 by 7 times of L. Okay, so how much this bar magnet, this monopole is inside from the total length, you can call it as L by 14. From this side, if you go L by 14 distance, you will get the first pole 14 actually. From here also L by 14. So what is the real length? That is 6 by 7. Okay, is it clear?
Yes.
Okay, that is the thing. Wait, 6 by 7, what should be the value control? Yeah, it's the same actually. It's a 6 by 7. Exactly not, but similar to it. Okay. More specific, if you want to go, the more specific value should be the Lm. Basically, we say the total bar magnet is L, then Lm is the 6 by 7 times of L. Understood? Or more specific, 0.84 L. Specific value. Okay, more specific. But in decimals for better calculation, we write in this format. Clear?
Yes.
So whenever you are given a total length of a bar magnet, magnetic moment will you can call as m times of L. What is m? Single pole. And what is the L? L you have to keep Lm. Okay? What is the real distance? But you are given a total length. So if this is directly given, you can directly put it. If this is not given, L is given. What you can say 0.84 m L. Okay, clear? Let's
Yes.
go further and talk about magnetic field. So what is magnetic field? Due to motion of charges, okay, or directly you are keeping a magnet itself, or magnet, the reason can be written another way. The reason around a charge, a moving charge. I will discuss in later that how a moving charge is creating a magnetic field. Okay, we'll discuss this thing further. Just charge, particle, or magnet, in which its effect, magnetic effect, its in which its magnetic effect is formed, is spread, is known as Okay, just a second. I'm yeah, Krishna. So we call it as a magnetic field. Yeah. Let's move to the next. You know that when we talk about electric field, after that, electric field is very simple thing that we had a charge, and what is the reason, right? Till where you can affect field. It is similar to this. This is a north pole, okay? Although they have both poles. I'm just talking about north. Assume that there is electric field, magnetic field like this. Okay? So here you can feel its effect. Here you can, and so on. So on. Wherever you can feel, there is a magnetic field. More concerning topic was strength. Okay, so here you can call this the strength of magnetic field. Effect is fine. Here I am feeling the effect, but what's the magnitude, right? How effective it is. That's what we call the strength of magnetic field. It has some other names also. One is strength of magnetic field or magnetic field strength, either way. Okay. We can also call it as magnetic induction. Remember this thing, magnetic induction is also known as strength of magnetic field. Understood? Yeah, sir. Magnetic flux density. Wait, magnetic flux density. It's actually you can call the same for electric flux density because if you could remember what is electric flux? Flux is nothing but electric field passing per area, right? So what is electric flux? Electric electric field is nothing but flux and how to calculate density. Density is basically some quantity divided by its geometry and what geometry this flux is containing area. So divided by this, it gives you electric field. Similar here also. If if I say this is an area, okay, this is some area, and from here some magnetic field is passing out. Okay, so we will call that as a flux. We will calculate flux. What is the flux? Magnetic flux. We will call that magnetic field. Okay, what is whatever the magnetic field is there? Strength of magnetic field. Okay, what is the strength of magnetic field and area? So if I ask you what is magnetic flux density, what is magnetic flux? If you divide it by the area, both sides, right? So what you have got magnetic flux. Okay, that is very simple. Magnetic flux and flux density is a different thing. Okay, when you talk about the flux, you are multiplying thing with area. When you take flux with the density, you are just talking about the thing itself. Okay, that's
Yes.
the whole thing is all about. These are some. Okay. What does all these things represents? It represents. It represents how strong. Okay, how strong or how strong The effect is if magnetic effect is very high, then you can say magnetic field is very high. If magnetic effect is less, field is less. Okay? Always keep difference with magnetic field and field strength. Both things are different. Understood? Field is just an area where you can have its effect, but how effective it is, that is known as a field. Okay, strength basically. Okay, generally strength. And the representation of that is basically B. This B generally represents all these things, all these factors. We can represent it by the B itself. Okay, we can't use M everywhere, right? We have already used two where one we were saying monopole and the capital we were saying what is it? Magnetic dipole. Right? In the future, we'll be studying about the magnetization on this where again we will be using some other concept of M itself. Okay, although if you could remember, dipole was represented by small p. So ideally, we should be representing monopole, this magnetic dipole with this small m itself, but we are using m as a monopole, so we are not using that convention right now. Okay, it's all about the convention. You should just know the concept itself. Clear? Any doubt? So
No,
yeah,
sir.
if your magnetic field effect is zero, zero means to say why the effect is zero. If zero is effect, it means strength is zero. Okay, so wherever, even though it is wherever in book, if the values are written as magnetic field is this, you should understand that effect is nothing but an area, right? Reason. So if it has given a value of effect, it means it has given the value of strength, okay, not just the field. Because for a field, just an area, you can't have that. You can't just give a value of some area, okay. Reason. Will if I ask you about the unit, so yeah, Kirtana, look, this is one thing, but we'll discuss the unit in a separate way. But let's explain it once. If you could remember, assume there was an electric field, okay, and if I keep a charge over this, if I keep an charge in this region, so you could remember we had a force on this charge, right? What was the force? The charge itself and whatever the electric field is, right? This is the thing we have. In a similar case, assume I am keeping my magnet, although magnet does not have a monopole, assume I am keeping both of them. I am keeping this into a magnetic field region. Okay? So let's talk about what is the force on this north pole. Although the force will be on both, I'm just concerned about a force. Like I just wanted to derive a unit. So I'm saying, assume what is the force on this. I will say force is nothing but m times of magnet. Okay. All right. So I'm asking, what is the unit of this? Wait, do I know the unit of force? Yes, I know. What is it, Newton? Do I know the unit of this monopole? Basically, what I can say, magnet pole strength. We say the pole strength is nothing but ampere meter. Look, this is meter. Okay. So can I get the value of B? Yes. B is nothing but Newton by ampere meter, and you can further call it as Newton and per ampere per meter. Is it clear? SI unit of magnetic field strength. Any doubts so far?
No, sir.
I hope not, right? Although, although the one who was the reason behind studying all these things, the person was known as Tesla. Okay, he was a Tesla. So basically, if you just further rewrite the same thing also, what you can rewrite it? What is Newton? Newton is nothing but kg meter per second square, right? You have ampere meter. Can I say, let's remove this ampere, that's meter. What you are going to get? The better unit you have derived from here now is kg per ampere, okay, per second square. This is what you have done. Also, the better way of writing the same thing is Tesla. Understood? Just like for a Newton, because was the one who derived this force and right. So we call it as Newton. The what is it? The unit of force is Newton. Although the Newton is all this force is also written as kg meter per second. Similarly, you can read at the magnetic field as kg per ampere per second square, but the unit is Tesla. Clear? Any doubt?
Yes. No, sir.
No doubt. Okay. So yes, yeah, Kirtana, this is all for the today's discussion. Okay. By this, I will be ending the discussion. In the next class, we'll be studying the rest of the part. Okay, about this magnet. So if you have any doubt, please let me know, or else we can end the session like this.
No doubts.
No doubt. Right? Okay, we'll be ending the session then. So yeah, good one.